Alright guys, today we're going to be going through our Unit 3 review. Our learning target today is I can write 2-column proofs and solve other problems involving triangles. So let's go ahead and get started. So for this first one, we're given that AB is perpendicular to BC, that DC is perpendicular to BC, and that angle 1 and angle 2 are congruent. So we're going to just go ahead and start by writing out our given information. Now, from here we're going to go ahead and focus on perpendicular. So I know if two segments are perpendicular to each other, that they will intersect at 90 degrees. So therefore angle ABC is 90 degrees and angle DCB is 90 degrees, or they're right angles. So angle ABC and angle BCD are right angles because if two segments are perpendicular, then they intersect each other at 90 degrees. Now, from here, if these are both right angles, that means that they should be the same measurement, so they're congruent to each other. So I can say that angle ABC is congruent to angle DCB, and the reason that we can say that is because all right angles are congruent. Now, from here, we also have these two base angles being congruent, angle 1 and angle 2. And if these two angles are congruent, that should mean that EB and EC are congruent to each other as well. So BE is congruent to CE because if base angles are congruent, then legs are congruent. Now from here, I'm going to go ahead and say that these two green angles are congruent to each other as well, angle ABE and angle DCE. And the reason I can say this is because if these two blue angles are congruent and the two red angles are congruent, well, what would happen if I took the red angle from the blue angle? Well, I'd be left with the green angles. So all we're doing here is we're subtracting. We're subtracting the red from the blue, and that will leave us with the green. So the reason that these two angles are congruent is because the subtraction property. Now, from here, if I focus on these two smaller triangles, this left triangle ABE and this right triangle DCE, then we should be able to prove that these two triangles are congruent. We just need one more thing. Now, looking at these two figures, I see vertical angles. I see angle AEB is congruent to angle DEC because vertical angles are congruent. And since those two angles are formed by intersecting lines, that would mean that those two angles are congruent and vertical angles. Now from here, we can say that triangle ABE is congruent to triangle DEC. And the reason that we can say that triangle AEB is congruent to triangle DEC is angle, side, angle. So those two triangles are congruent by angle, side, angle. Now, if the two triangles are congruent, then we should be able, and I can't say that the full thing is congruent, but I can say that AE is congruent to ED, because those are corresponding parts of those congruent triangles. So if triangles are congruent, then the corresponding parts of those congruent triangles are also congruent. Now, looking at this, what would happen if I add the purple segment and the red segment? Well, then I would have segment AC. If I did the same thing on the other triangle, I added DE and EB, I would also have segment DB. So if I do that, then these two segments would be congruent. AC is congruent to DB. And that only happens if I add these two segments together. So they are congruent by the addition property. And with that, this proof is now complete. All right, let's try out our next one. This time we're given circle O, and we're given that OG is perpendicular to FH. We would like to prove that FG is congruent to GH. So to get started on this, we're going to go ahead and start with our given information. Circle O and OG is perpendicular to FH. Now, from here, if we have perpendicular segments, I know that they're intersecting at 90 degrees. So angle OGF and angle OGH are right angles because if two segments are perpendicular, then they intersect at right angles. Now, if these two angles are right angles, then of course they're congruent to each other. So OGF is congruent to angle OGH because all right angles are congruent. Now, the only other given information that we have is circle O. And the only thing that we can do with circles is radii. But I don't see any radii on this circle. And again, a radii goes from the center to the edge. So we're going to actually create some radii. And with these radii, they're going to go from the center to the edge, but we want them to make triangles. So I'm going to create segment OF and segment OH. So draw segment OF and segment OH, and the reason that we can do that is any 2 points determine a line, ray, or segment. Now, since both of these go from the center of our circle to the edge, they're both considered radii. So I can say that segment OF is congruent to OH because all radii in a circle are congruent. And that's exactly what's happening here. Now, the last thing that we need is something that's shared by both triangles. And I see that GO is shared by both triangles. So I can say that GO is congruent to itself, and of course that's always going to be by the reflexive property. Anytime anything's congruent to itself. Now, looking at this, we should have enough information to prove that these two triangles are congruent to each other. We have a right angle, so that should automatically be telling us HL is on the table. So if I look at this, we have a right angle, we have the hypotenuse, and we have a leg. So that is enough information to say that triangle FOG is congruent to triangle HOG by HL. Now, of course, this would not be angle side side. That's not a postulate for us. It needs to be HL. Now, at this point, if the two triangles are congruent, then the corresponding parts are also going to be congruent. So I can say that segment FG is congruent to segment GH, because if the triangles are congruent, then the corresponding parts of those congruent triangles are also congruent, or CPCTC. And with that, this proof is now complete, because that's what we were setting out to prove. All right, next up. This time, we're given that segment PK and segment JM bisect each other at point R. We want to prove that PJ is congruent to MK. So to get started, we write out our given, PK and JM bisect each other. And then on top of that, we're going to go ahead and focus in on that bisection. So if they're bisecting each other, that means that they're cutting each other in half. So PR is congruent to RK and JR is congruent to RM. And the reason that we can say that is because if two segments bisect each other, then they're cutting each other in half. Now from here, is there anything that's shared by both triangles or any vertical angles or anything like that? Well, yes, angle 3 and angle 4. These two are vertical angles. They're formed by crossing lines. So angle 3 is congruent to angle 4, and the reason that we can say angle 3 is congruent to angle 4 is because all vertical angles are congruent to each other. So vertical angles are congruent, so angle 3 and angle 4 are congruent. Now from here, we can say that the two triangles are congruent. Triangle PRJ is congruent to triangle KRM. And the reason that we can say that, and this should be an M, not a J here, the reason that we can say that is side, angle, side. So those two triangles are congruent by side, angle, side. Now, if the two triangles are congruent, well, segment PJ and segment KM are both on those triangles, so I can say that segment PJ is congruent to segment MK by CPCTC. Because if the triangles are congruent, then the corresponding parts of those congruent triangles are also congruent. All right, let's move on to our next proof. This time, we're given circle P, and that PR bisects angle KPM. We would like to prove that PR is a median. So if PR is a median, we know that medians intersect at the midpoint of the opposite side, so R would have to be a midpoint. For R to be a midpoint, that would mean that KR and RM are the same length. So that's what we're going to be working towards. If we can prove that KR is congruent to RM, that would prove that PR is a median. So to get started, we write out our givens, circle O, and that PR bisects angle KPM. Now, from here, if PR is bisecting angle KPM, that would mean that's cutting this angle in half. So angle KPR is congruent to angle MPR, and that's due to the definition of an angle bisection. If a ray is bisecting an angle, then the angle is being cut perfectly in half. Now, at this point, we're also given circle O. Now I see that we have a couple radii here. So I can say that those radii are congruent. Our radii are segments PK and segment PM. So I can say that PK is congruent to PM because all radii in a circle are congruent. The last thing that we have here is something that's shared by both triangles, and that's segment PR. Segment PR is congruent to itself by the reflexive property, which will allow us to say that these two triangles are congruent. So reading our congruency statements, we have a side, an angle, and a side. And that's enough information. So we can now say that triangle PRK is congruent to triangle PRM, and again that's by side, angle, side. So those two triangles are congruent by side, angle, side. Well, if those two triangles are congruent, then I can say that KR is congruent to RM because those are corresponding parts of those triangles. So KR is congruent to MR, and that's by CPCTC. Corresponding parts of congruent triangles are congruent. Well, if KR is congruent to RM, that would mean that R is right in the middle of that segment, which means that R is a midpoint, which means PR is intersecting through the midpoint, which means that PR is a median. So we can say at this point PR is a median, and the reason that we can say that is if a segment divides the side of a triangle into two congruent parts, then the segment is a median. We can see that's intersecting right at the midpoint here as well. And with that, this proof is now finished. All right, next up, triangle HGF is equilateral. If angle F is equal to x plus 32 degrees, angle H is 2x plus 4 degrees, solve for x and find the measure of angle G. Well, first off, it's equilateral. And equilateral triangles are the same as equal angular triangles, so therefore all sides are congruent and all angles are equal, meaning that each angle is 60 degrees. So right away, angle G is 60 degrees. Now from here, if I want to find out what x is, well, I know that each of these angles is 60, so I can say that angle F is 60 degrees, and it's also equal to x plus 32. So 60 is equal to x plus 32. That will allow us to solve, and I could have used angle H as well, done the same thing. 60 is equal to 2x plus 4. And I did both of these here, so again, you only need one or the other, either the green or the red here. And regardless, you would have gotten the same answer. Now, I wanted to check mine, so I did both, and I got 28 for both, which means I did it correctly for sure. So x is equal to 28, and the measure of angle G is 60. Now, if the perimeter, the distance around triangle HGF, is equal to 6y plus 24, and segment HG is just equal to 3y minus 7, what would be the perimeter of this triangle? Well, again, it's an equilateral triangle, so each side is going to be 3y minus 7 in length. And therefore, I can just add up all those sides and set it equal to our perimeter. So 3 sides times the same length, which is 3y minus 7, because again, equilateral, is equal to the perimeter of this triangle. Multiplying the 3 through the parentheses, we get 9y minus 21 equals 6y plus 24. I'm going to go ahead and subtract 6y from both sides, giving us 3y minus 21 equals 24. Adding 21 to both sides, we get 3y equals 45. And then dividing both sides by 3, we get y is equal to 15. But we're not trying to solve for y. We want to solve for the perimeter. So we got to plug it back in for y in our perimeter. So our perimeter is 6y plus 24. If I plug in 15 for y, I have 6 times 15 plus 24. Well, 6 times 15 is 90, plus 24 is 114 units. So our perimeter is 114 units, our y variable is 15, our x variable is 28, and the measure of angle G is 60. And with that, this entire problem is finished. All right, next up. Here is our next proof, and this one's going to be a little bit longer. So we're given that AC is congruent to BC, and we're also given that angle 1 is congruent to angle 3. We would like to prove that triangle DFE, the small triangle right here, is isosceles. So to get started, we have our given information. AC is congruent to BC, angle 1 is congruent to angle 3. Now, I'm going to use this information of base angles being congruent to further this proof right here. So I'm going to now say that CD is congruent to CE. And the reason I can say that CD is congruent to CE is because if base angles are congruent, then legs are congruent. So if base angles are congruent, then legs are congruent. Now, if I look at this, I have this green side length and this blue side length now. So from here, I'm looking at triangle ACE. So that's the triangle that I want to prove congruent, triangle ACE congruent to triangle BCD. So these are the triangles I want to work with. Now looking at those two triangles, they both share angle C. So I can say that angle C is congruent to itself by the reflexive property. Angle C is congruent to angle C by the reflexive property. Now we can see these triangles a little bit clearer. So looking at this, I can now say that triangle ACE is congruent to triangle BCD by green side, purple angle, and then blue side. So again, triangle ACE is congruent to triangle BCD by side, angle, side. Now, if those two triangles are congruent, I'm trying to prove that this triangle in the middle, triangle DFE, is isosceles. So I'm going to use information to help further along this smaller triangle. Well, the only thing attached to that smaller triangle from our big triangle is angle CEA and angle CDB. So I'm going to go ahead and say that those two angles are congruent. Angle AEC is congruent to angle BDC, because if the triangles are congruent, then the corresponding parts of those congruent triangles are also congruent. Now, what would happen if I took away the red angle from the gold angle? Well, I'd be left with angle FDE, and I'd also be left with angle FED. So that's exactly what we're going to do. I'm going to say angle FDE is congruent to angle FED, and all I did was I took away the red angle from the yellow angle. Well, what's a good property for that if I'm taking something away? Well, that would just be the subtraction property. I'm just using angle subtraction. So I'm taking angle 1 away from angle AEC and angle 3 away from angle BDC. And again, we can see that both of these are already in our proofs for statement number 6 and statement number 2. Now, from here, that will leave us with these two angles, angle FDE and angle FED. And they're congruent. Well, those are our base angles. So if the base angles are congruent, then I can say that DF, segment DF, is congruent to segment FE. Because if base angles are congruent, then legs are congruent. Lastly, if two legs of a triangle are congruent, then we say that that triangle is isosceles. So triangle DFE is isosceles, because if two legs of a triangle are congruent, then it is isosceles. And with that, this proof is now finished. All right, let's go ahead and continue on. Next up, this is a shorter proof. Triangle ZWX is isosceles with base WX. And we know that WR, ray WR, it bisects angle XWZ, and XR bisects angle WXZ. We want to prove that these two angles, angle XWR and angle RXW, are congruent. So of course we start off with our given information. Now, from here, if this is an isosceles triangle, I know that the legs are going to be congruent. So they already tell me that this is the base, WX, so I can say that ZW is congruent to XZ, because that's the definition of an isosceles triangle. If a triangle is isosceles, it has two legs, segments that are congruent. Now, from here, if the legs are congruent, then I know base angles are congruent. So I can now say angle ZWX is congruent to angle ZXW. And again, that's because if legs are congruent, then base angles are congruent. Now from here, our goal is for these smaller angles, angle XWR being congruent to angle RXW. So, I see the word bisect written twice. That's a big hint for us right away, because if I see bisect written twice, that opens up division and multiplication properties. Now, I'm going from the big angle to the small angle. So therefore, this is going to be division property. So at this point, I can go ahead and say that angle XWR is congruent to RXW, what we're trying to prove. And again, we're going from big to small, so this is by the division property. And with that, this proof is now complete. All right. I believe this is our final proof. We're given that angle AEC is congruent to angle BED, and that AE is congruent to ED. So I went ahead and drew that on our picture. Now, with these two green angles, I see that they kind of share this common middle angle here, angle BEC. So I can go ahead and say that angle BEC is congruent to itself by the reflexive property. And the reason I want to do that is because I, again, want to prove that this triangle on the left and this triangle on the right are the same. So what would happen if I took away this middle angle from the two green angles? Well, I'd be left with angle AEB and angle CED. So let's just do that. So I have angle AEB is congruent to angle CED, and all we did was we took away the gold from the green. So that is subtraction property. So that's why those two angles are now congruent. Now from here, we have two legs of a very large triangle that are congruent, which means that our base angles are congruent. So angle A, here's where that information came from. So angle A is now congruent to angle D, because if legs are congruent, then base angles are congruent. From here, we have enough information to prove that the two triangles on the left and the right are congruent to each other. So triangle ABCD EB is congruent to triangle DEC by angle, side, angle. If the two triangles are congruent by angle, side, angle, that means all corresponding parts are also congruent. So AB will be congruent to CD, because if the two triangles are congruent, then those corresponding parts of the congruent triangles are also congruent. And with that, this proof is now finished. All right. Next, we're moving towards some factoring polynomials here. So triangle ABC is isosceles with base BC as the base. Find the possible values of x. Now, if BC is the base, that means that angle B and angle C are base angles, which means that they're going to be congruent. So I can say x squared plus x equals 56. Now from here, this is not standard form for a polynomial, so I need to get everything on the same side. So I'm going to subtract 56 from both sides, which gives me x squared plus x minus 56 equals 0. From here, I'm going to multiply my a value, the number in front of x squared, times my c value, my constant. So 1 times negative 56 is negative 56. From here, I look for numbers that add to be our middle term, positive 1, and multiply to be negative 56. So I list out all the numbers that multiply to be negative 56. The ones that add to be positive 1, well, adding all of these pairs together, the only one that adds to be positive 1 is negative 7 and positive 8. So within my double bubble, I'm going to go ahead and put negative 7 and positive 8. And of course, it's still going to be set equal to 0 down here. So x minus 7 times x plus 8 equals 0. Now, if it has its own bubble, it gets its own equation. So I have x minus 7 equals 0 and x plus 8 equals 0. Those will give me the answers x is equal to 7 and x is equal to negative 8. Now, if I want to check my work, I plug these back in and see if they work out. 7 squared will give me 49, plus 7 will give me 56. So if these are both 56, that's true, it's isosceles. Plug in negative 8. Negative 8 squared is 64. 64 minus 8 will give me 56. Both answers work in this case, so therefore both answers are correct. All right, let's try another one. This time we have x squared minus 6x, and then 55 is our other angle. Same type of thing happening. This time AB is congruent to AC, which means that it is automatically an isosceles triangle, because if legs are congruent, then base angles are congruent. So this time we have x squared minus 6x equals 55. Subtracting 55 from both sides to put it in standard form. X squared minus 6x minus 55 equals 0. From here, I multiply a times c. That'll give me 1 times negative 55, which is negative 55. And then at this point, we're going to go ahead and find numbers that add to be negative 6, our b value, and multiply to be negative 55, our c value. So, doing that, the numbers that multiply to be negative 55, I have 1 in negative 55 and 5 in negative 11. So the numbers that will add to be negative 6 out of those two are 5 and negative 11. So I create my double bubble. The variable that comes first is x in both bubbles always, or whatever variable that we're dealing with. And I take my positive 5 and my negative 11 and I plug them in. Of course, it's still going to be set equal to 0. That hasn't changed. If it gets its own bubble, it gets its own equation. So x plus 5 equals 0. X minus 11 equals 0. Solving for both of these, we get x equals negative 5 and x equals positive 11. And then we plug them back in to see if they work. Negative 5 squared is 25. Negative 6 times negative 5 is positive 30. 25 plus 30 is 55. Negative 5 works. Plugging in 11, I'd have 121 minus 66. Well, 121 minus 66 is 55, so both answers work. We did it correctly, and we can see that this is still isosceles. All right, next up. You guys are going to have 7 of these questions tomorrow. So for each statement, write A for always true, S for sometimes true, or N for never true. 2 triangles are congruent if 2 sides and an angle of one are congruent to the corresponding parts of another. So this is sometimes true. And the reason for it goes to side, and angle, side, angle, and all these different postulates. So if I have 2 sides and the angle is included in between the 2 sides, that would be side, angle, side. But what if it's not an included angle? What if my angle's on the outside of the 2 congruent side lengths? Well, that would be angle, side, side, which is not one of our postulates. So since it's true when it's side angle side, but it's not true when it's side side angle, that's why this is only sometimes true. So it's not an always true statement, and it's not a never true statement. It's sometimes true. If two sides of a right triangle are congruent to the corresponding parts of another right triangle, then the triangles are congruent. This one is always true. The reason that this is always true is because it's a right triangle, and that changes the rules a little bit. For a right triangle, we can have side angle side, or we can have HL. So again, if my angle is not included, that gives me hypotenuse and leg this time. If it is included, that gives me side angle side. So this will always be true, and it's because it's a right triangle. That's what makes it true. All right, next up, letter C. All three altitudes fall outside the triangle. So again, an altitude is drawn from a vertex and intersects the opposite side at 90 degrees. So having all three altitudes fall outside the triangle, that is impossible. That is never going to be true. At most, you will get two altitudes that fall outside of a triangle, which we see in our obtuse triangle over here. With a right triangle, two of the altitudes will lie on the triangle, one will fall inside. And then for an acute triangle, all three fall inside. But three altitudes will never fall outside the triangle. That's not possible. At most, only two altitudes will fall outside the triangle. And of course, that's only occurring in obtuse triangles. No other triangles will see two of them fall outside. All right, letter D. A median of a triangle does not contain the midpoint of the side to which it is drawn. Well, this is never true either, because the definition of a median is a segment drawn from any vertex of a triangle through the midpoint on the opposite side. So therefore, by definition, this is false. A median has to cross through the midpoint of the opposite side. Letter E. A right triangle is congruent to an obtuse triangle. This is never going to be true either. A triangle can either have a right angle or an obtuse angle. It can't have both. It can't have both. And the reason for that is if there's 180 degrees in a triangle, which we know is true, we can't go above 180 degrees. Well, if I have a right angle, that's 90. If I have an obtuse angle that's greater than 90, well, 90 plus 90 is already 180. So therefore, this is never going to be true. You're never going to have two right angles in a triangle, and you're never going to have a right angle and an obtuse angle in a triangle. It's just not possible. So if a triangle has an angle of 90 degrees, it can not also have another angle that's 90 degrees or an angle that's larger than 90. Because again, 90 plus x plus y is equal to 180. That means my other two angles need to equal 90 when they're added together. For an obtuse angle, both my angles need to be smaller than 90 when added together because we already have that obtuse angle. All right, and letter F. If segment AB is congruent to segment BC in triangle ABC, then angle BAC is congruent to angle ABC. Well, for this one, I encourage you guys to draw it out. If I draw this out, triangle ABC, and I draw exactly what they tell me, AB is congruent to BC, angle BAC is congruent to angle ABC. Well, automatically looking at this, I can see that this is not always going to be true. This is only sometimes true. And the reason that it's sometimes true is if this is an equilateral triangle, it will work. If it's any other triangle, it does not work at all. So what I'm saying is that this side length and this angle also need to be congruent in order for it to work. If that's not the case, it will never happen. So if triangle ABC is equiangular, meaning all angles are 60 degrees, then the statement is true. If not, the statement is false. All right. That is it for our always, sometimes, or never true questions. Again, you guys will have 7 of those on the test. In the diagram, if segment BC is congruent to segment CD, as we can see in the diagram, in order to prove that triangle ABC is congruent to triangle EDC by HL, which sides must be congruent? Well, HL is for hypotenuse leg. And looking at this, we already have a leg. We have BC and CD. Those are legs. We already have a right angle, so all we need is the hypotenuse. Well, the hypotenuse is opposite the right angle, so we can draw arrows from our right angle going towards it. So we need segment AC and segment EC. If those two segments are congruent, then those two triangles are congruent by HL. In a triangle, what name is given to a line segment drawn from a vertex to the midpoint of the opposite side? Well, if it's going to the midpoint, by definition, that is a median. Medians will always go from a vertex to the midpoint on the opposite side, and we can see that's going to the midpoint because it's dividing the segment into two congruent segments. So that means that this point would be right in the middle. All right. If triangle PQR is congruent to triangle TWV, which of the following is not necessarily true? So, looking at this, the order matters in our congruency statement. If it's not in the correct order, then it's not necessarily true. So looking at this, P and T both come first. So letter A is true. Looking at letter B, VT. Well, V and T is first and third. R and P is first and third. So that is also true. Looking at letter C, QR. Q and R is second and third. W and T is first and second. This is not necessarily true. It could be true depending on the type of triangle, but it's not necessarily true. And let's check our final one just to make sure. W and Q. Well, Q is second. W is second. That is a true statement. So our correct answer, the one that is not necessarily true, is letter C. The rest of these are all true based upon where they're at in our congruency statement. All right. And here it is, just going through it once again. There we go. The lengths of the base and a leg of an isosceles triangle are in the ratio 3:2. The perimeter of the triangle is 105. Find the length of the base. So this is our last problem. We're going to start by drawing an isosceles triangle. And they tell me that the ratio of the base to the leg is 3:2. So if we're dealing with a ratio, each one gets a variable. So I have 3x for the base, 2x for the leg. So drawing this up, my base is 3x, my leg is 2x. And since this is isosceles, I know my legs will be congruent. So my other leg will also be 2x. Now, the perimeter, the distance around the shape, is 105. So I can say 2x plus 2x plus 3x equals 105. From here, combining like terms, 2x plus 2x plus 3x is 7x equals 105. Dividing both sides by 7, x is equal to 15. Again, we're trying to find the length of the base. So I plug it back into the base of my triangle, which is 3x, which will give me 3 times 15, which is 45 units. So our answer for the length of the base is 45 units. All right. So that is it for our review. If you guys have any questions, please let me know. I hope that you guys all do well on the test. And thank you guys so much for watching today. If you need anything else, again, please let me know. Have a great rest of your day, guys. Thank you.